All right. Today we're actually starting a new section. Good and bad. The good is that we're done with radicals for now. Bad is we're never done with arrow pushing. That's good too. Because you're gonna see arrows up. Organic, that's all we talk. So what I want to do is let me pull the handout. We have a new handout, and I didn't give it to y'all, but let me do this. Let me do four.
Literally, no.
Let me just show you.
But who's here?
Think,
Oh, it is. Okay, cool. What then? Okay, so I've been wanting to tell you, but I just didn't know how. And I'm just gonna flat out say it. I just don't want our friendship to like. You know, so I actually have this for you. Which one do you enjoy? Huh?
Make sure it's holding the whole conversation. So the handout is in Blackboard, is here. It's in module. Let me see, too much stuff in the way. It's in the next module. How does this shrink down like this? I think it's third. So if you click on third module in Blackboard, it's the substitution and elimination. This is going to be a quick section. It's not, you're not going into great detail because we're going to see this again in part 2 in a lot of detail. So yeah, so it's the handout is there. If you're on your laptop right now, you can go grab it. If you're here and you can grab it, that's fine. If you need me to send it to you real quick, I can do that. We'll get started. Yes, no, you want me to send it? Chase, Cameron? All right, cool. All right. So yeah, let me pull up my screen on my iPad. Y'all pray for that battery. I make the same mistake 2 days in a row. I don't know. I'm gonna make it work. The good thing is we've already kind of seen a glimpse of substitution and elimination, so that's going to make this a little bit easier to track. Let me pull it up here. And we'll get started. All right. So the whole idea, again, this section is dealing with substitution and elimination. Let me screen. All right, 1 second, it's coming up. All right. So. 26. All right. All right, so we're gonna talk about again substitution and elimination. And I'm gonna really pare this down because it's a very nuanced topic, but I'm gonna try to pare it down to the following. So we're gonna talk about identifying the nucleophile, leaving group, base. Right, the leaving group is common to both. Substitution and elimination both involve a leaving group. So we're gonna, that's one of the things that we want to learn is how to identify my nucleophile, my base, if it's an elimination, or my leaving group. Also, want to look at substrate structure. Is it primary, is it secondary, is it tertiary? That's going to be a big deal. So we look at substrate structure. We're going to look at solvent effects. Right? And the key there is going to be identifying what we call protic and what's aprotic. So protic solvents and aprotic solvents. That's going to be something that we're going to pick up from this. Protic versus aprotic, and then rate law. Right, you're going to learn about the rate laws for the different reactions. It's elimination or substitution. It changes based on the nature of the reaction. Right, there's a type of reaction that we're going to look at. It's SN2. There's a type of reaction we look at as SN1, and the rate law is going to be different for each one of those. So I'll just say here second order. The reactions we look at are going to be one of the other. Either going to be a first order or second order rate law. Last thing. Is the energy diagram. What does it look like? Is there an intermediate? How do we show it? Exothermic, is it endothermic? So on and so forth. We've seen all this stuff. Well, we've seen a lot of it before. And some of it is new. And so we're going to walk through it together. So what does the energy diagram look like for a reaction that has an intermediate as opposed to a reaction that doesn't? I'll answer that question. And but again, for now, I'm paring this down. I'm not going into all the gritty details about solvent. I'm not going into all the gritty details about the rate, things like that. But we're going to be able to, we're going to know what each one of those things are. And I guess we're going to also revisit the idea of what a transition state. All right, because the substitution and elimination reactions are going to have different transition states. And I think I showed you this already, but we're just going to just touch it again. All right, any questions so far? Everybody good? All right, let's go to the first set of reactions, and we're going to talk about first the SN2 reaction. All right, SN2 is substitution. Right, the N is nucleophilic. And the T is bimolecular. Right, that two tells you if it's first order or second order. Right, so you can make the assumption that if it's bimolecular, it's second order. The rate law is going to be second order. We'll touch that again in a minute. Right, just apply some logic. If it's SN1 or E1, then it's going to be first order. But don't worry about that part. I'm just throwing that out there. All right. So with SN2 substitution, right, it's also what we call a concerted mechanism. So write that down. That is concerted. So no enemy. No enemies. So the mechanism for the SN2, the rate determining step anyway, is going to be concerted. All right. Questions? Anybody have a question about anything?
Can you repeat what makes it second order again?
Okay, so when we say that it's bimolecular, I'm gonna show you too, but when we talk about the transition state, but when we say that it's bimolecular, that's indicative of the fact that there are two things participating in the rate determining step. So that's why we call it that's why we can say that it's a second order rate law. But we're going to talk about it when we look at the transition state. All right. Let me cut this and put it on another page so we can get this. All right, so let's look at the first reaction. And let me ask this question based on what we studied already. When you think about a substitution, what's happening? What was the definition I gave you when we talked about substitution? So you said, what's the first word? Swap. Good. So we're going to swap out some functional group or atom with another functional group or atom. Yes, 100% agree with that. So up here, when we're looking at this reaction, we need to be able to identify, and this is another reason why we did the other exercise first. Well, we found the nucleophile, then we found the electrophile, and then we put the arrows in, and so on and so forth. We're going to do the same thing here. All right, this is my nucleophile. Right, it has 3 lone pairs, it's negatively charged, and that's a dead giveaway that it's a nucleophile. So that's the first step in a substitution. If you have to predict the product, the first step is identifying everything you need. So what's the nucleophile? What's the electrophile? And I think I sent y'all an alkene video, didn't I? My fault. But just hold on. That's my fault. I didn't open 3A. I was just so excited about getting to alkenes. My bad. But I'll send you the right stuff today. You have my word on it. All right, so that's my nucleophile. By default, what is the alpha halide over here? That's my electrophile by default. Once I find the nucleophile, the other molecule is by default the electrophile. And substitution, when we're talking in terms of substitution and elimination, we call this electrophile, we call it the substrate. call it the substrate. Nucleophile is ubiquitous. We can say that in any context, but in the context of substitution and elimination, we call the electrophile the substrate. All right, now here's the question. What's going to happen between the nucleophile and the electrophile? What happened when we were studying this before? What does the nucleophile do to the electrophile? Does it attack it? How? All right, what's the content, well, not content, what's our mode of conversation for organic? Like, how do we talk? We talk with arrows, right? So to show the nucleophile attacking an electrophile, I need to show arrow going where? From here? Not there. There, is that right? Not the Amazon arrow, but it's close enough. All right, and then what else? Break the carbon bromine bar. Is that right? That's how we swap those out. We don't just like, it's not like Legos where you just pluck off an atom and then put another one on. You swap them out because the nucleophile actually forces that bromine out. So what is bromine in this context? Leaving group. I'm gonna abbreviate that as LG. Bromine is my leaving group. Your leaving group is always going to be more than likely it's going to be the most electronegative atom or the most electronegative functional group in the electrophile. Here's a question that I didn't put that on our list, but it's in the conversation that we're having. How do you know how if a leaving group is good or bad? Anybody want to take a stab at that? How do you know if it's a good leaving group or if it's a bad leaving? Let's draw the products and then maybe that'll help better. So what is now bonded to excuse me, where bromine is? What's there now? You had it. I saw you writing. The sulfur. All right. We want to write that over here. Is that right? Anybody not see that? That's one of the products. And then what else? Did bromine disappear? No, it's still in solution. So we're going to put that in plus Br. Now bromine in this case looks a lot like a conjugate base, doesn't it? Remember when we did acid-base chemistry and we did proton transfer from the acid and we got left with something negative that was just hanging out. So bromine looks a lot like a conjugate base. So your leaving group, you can judge it on the same criteria as you would a conjugate base. Right? We used hires then, and it's the same idea. So you can judge your leaving group ability based on using the pKa of its conjugate acid. Somebody tell me what the pKa of the conjugate acid of, well, not pK. What's the conjugate acid of Br minus? HBr? Yes. Yeah, it will be HBr. So hydrogen, yes. So any leaving group, you can figure out if it's good or bad based on the pKa. And we have a chart for that, which I'll show you later. All right, questions about that example? Let's talk a little bit more about let's talk more about the reaction itself, right? So for SN2, it prefers to happen on a primary carbon, which we're going to talk about why in a second. Secondary carbons work, but primary is preferred. And that's really because of the mode of attack of your nucleophile, which I'll show you in a second. All right. And then the solvent. Let's talk about the solvent. The solvent here is acetone. Acetone is what we would consider a protein. What aprotic basically means in a nutshell is that it's non-acidic. It cannot give up H plus. All right, it can't give away H plus. It's not like an alcohol or some acid or water that can give away H plus. So that's what aprotic means. Cannot donate H plus. SN2 reactions happen better in aprotic solvents. All right, I'm gonna talk about that too. Go ahead. What I just said about SN2, they happen faster in aprotic solvents. All right. So it's facilitated by aprotic solvents. I'll talk about that too when we talk about the rate law and the transition state. Any questions about anything so far? So we've seen the mechanism, the arrows, the outcome. We know the solvent has to be aprotic, and I'm gonna talk about that in a second. And we know that it prefers to happen on a primary carbon. All right, now let's talk about what the transition state looks like for SN2. And from that, we can talk about the rate law, and we can go back and talk about the solvent also. All right, so the key to the SN2 reaction is how the nucleophile attacks the electrophile, right? In an SN2, the nucleophile always attacks from the opposite side of what a leaving group is. It attacks the opposite of the leaving group. That's very important because that leads to some other characteristics of the reaction. We're not really going to get into them, but it always attacks opposite of the leaving group. So if this is my substrate, I'm kind of abbreviating that ring, right? Because we haven't talked about chairs and boats yet, so I don't want to draw that. That's my substrate. The nucleophile is coming from here. Right? Everybody agree with that? So the arrow here to here, and then here's my bromine. That's my leaving group, so it's leaving with a pair of electrons. What's that called when I break a bond like that and give both electrons to the same atom? Anybody remember? Homo is 1 and 1. So it's heterolytic. Good. And then what is this called when one atom brings both electrons? Heterogenic. Good. So this is the mechanism. It always happens like this. So the nucleophile is coming in from the backside, the leaving group is leaving, it's all happening at the same time. So the way I illustrate this in terms of transition state, I'm just gonna copy this. You've seen this before because we talked about transition states recently. So it's like this. This bond is being formed. This bond is being broken. This is my transition state. Forming bond between the nucleophile and the substrate, and a breaking bond between the substrate and the ligand. Substrate. That's break. All right, questions about that part? So this is why we say that the reaction is bimolecular. Because you can see it from the transition state. The nucleophile is involved. This is my nucleophile. And the substrate is also involved. Right? And this is also the rate determinant step. So we call, this is what the rate law is going to be based on. So in the rate determinant step, that's RDS, rate determinant step, the nucleophile and the substrate are involved. That's why we say it's bimolecular. That's what the two means in SN2. That in the rate determinant step, you got two species that are involved in that rate determinant step. Right? Questions? Any questions so far? Let me know if I'm moving too fast, too monotone, too slow, whatever. Can everybody hear me okay? That's logged in. We got 10 people absent on a Wednesday. Actually 14 people. We got 34 people in this class. 20 online and 4 present. That's great. Really 19 online because I count as participant on Zoom. Involved. Sorry. All right. So for the SN2, the way we write out the rate law is that the rate K times the substrate and the concentration of the substrate and the concentration of the nucleophile. That's how we write that out. K times the concentrate. K is the rate constant. Y'all remember that from Biswas or Reeves? If you took Reeves, you take Reeves. So K is the rate constant, concentration of the substrate, concentration of the nucleophile. Those two things determine the rate. And the rate is based on the slowest step in the reaction, which is the rate determining step. And for SN2, that rate determining step is going to be attack of the nucleophile and loss of the leaving group. Both of those things matter. All right, any questions? So for this reaction, we've looked at the mechanism. We've identified the leaving group, identified the nucleophile, identified the substrate. We have looked at the outcome, the products, and the transition state. The only thing I want to talk about further, a little further, is the solvent. Yeah. The only thing I want to add is the solvent. Right. So when you hear the word solvent, what do you think? Anybody? When you hear that term in terms of chemistry, what do you think? Anybody? You eat ramen? Don't, do you? Do you eat ramen? No? Reagan? You eat ramen? Do you, Cameron? When you cook it, how do you cook it? You just put it in the pot and turn the stove on? Add water. You need a medium, right? So the solvent is the medium in which the reaction is running. I had a cousin one time who was staying with me. She was a traveling nurse. She blew up my microwave because she put a package of ramen in there with no water. Blew the microwave up, smoked up the house, and that was her ticket out of the house. She couldn't stay there anymore. She had to go. But the salt, you can do reactions without solvent. That's called doing them neat. For the most part, you need a solvent. So in this case, our solvent, this is gonna lead us to the discussion about the energy diagram. The solvent was acetone, is that right? Right, so I'm doing this in acetone. Excuse the choppiness. That's because I got the thing plugged in. So I'm doing it in acetone, which is a protein. Right, that's good. This is the structure of acetone. Right, so it's polar, apolar. The polar part is good too, because remember in the transition state, the nucleophile is negative and the leaving group is going to be negative when it leaves. So the overall charge is negative. So everything has a charge. So polar solvents are good because they help to minimize the charge. Right? If I did this in ethanol, the reaction will slow down. I'm going to show you why. Ethanol is not aprotic. Ethanol is protic. Right? Aprotic means cannot donate H plus. So by default, protic means what? It can. So all alcohols are what we call protic. Water is protic. All your acids are protic. They can give up H plus. So if I did this in ethanol, my nucleophile which is negative, will get surrounded by protons. They basically make a cage around my nucleophile, a trap. Right? So if I ran the reaction in a protic solvent, a nucleophile is going to get trapped. Right? Do you think that nucleophile is going to have the same reactivity if it's trapped in a cage like that, or is it going to be less reactive? Less reactive. Just like, let me give you a perfect example. Hope you don't mind me using you as an example. You got a ball coming to you, right? And you go to for the kill, but one of your teammates grabs your arm. Are you gonna get that kill? You're not, right? That's what happens. So when that solvent surrounds your nucleophile, it's not as reactive. It cannot get to the electrophile. This is called solvation. Right? So the protons from that protic solvent around the nucleophile, and they basically kill its reactivity. Right, that makes the rate go down, because the nucleophile is a part of the rate determining step, and it's not available, that's gonna slow the rate down. Right, so the rate is gonna slow way down if that nucleophile gets solvated like that. So that's why you do this reaction in aprotic solvents. If you do it in a protic solvent, it's gonna take forever. All right? Let's think about this in terms of an energy diagram. Right, I'm gonna do a red curve and a blue curve. Let's just say for the sake of the discussion that this is a exothermic reaction. So the red curve is aprotic, and then the blue curve is protic. Which one of those has the higher activation energy? Let's look at it. Same transition state, that doesn't change. All right, what do you think? I'll give you time to write. Go ahead, take your time. This is the last thing we'll talk about, so I want you to get this down so we can discuss it. If you're online with us, take your time, write it out, and then I'll give you a few seconds to write it out so we can discuss it. But the good thing is you've seen energy diagrams before, right? It's not the first time you've been introduced to this, so this is good. And I'll go ahead and lay time on the x-axis, energy on the y-axis. All right, I'll talk about two things with this energy diagram. First, we'll talk about the solvation part, and then we'll come back and talk about one other piece that it represents. All right, which of those two reactions, which one is faster? The one in the aprotic solvent. Why?
It has a sign between where it originally started and where it activated.
So the gap between the transition state and the starting material is shorter, isn't it?
Yes.
Which means the activation energy for that aprotic solvent, for the reaction done in the aprotic solvent, is lower. What about the protic? What happens to the activation energy? Goes up, right? It increases. So in a protic solvent, the activation energy is going to increase because of that solvation. So your nucleophile is here, and it's trapped by these protons. Right, that nucleophile being solvated relaxes. So it's not as I hate to use the term aggressive, but it's not as aggressive. So it gets relaxed, the energy goes down. By that same token, the activation energy goes up, and that's not good. All right, we'll stop here. We're gonna pick this up on Friday. Any questions before we log out or before we leave? All right, we'll stop. We'll pick it up Friday. If you have questions in between, just email me, and I will send the